In this video, we'll walk through an example that shows how to use the groundwater simulation tool in VO for wetland modeling. Our goal is to understand why simulating groundwater is important, how it improves post-development analysis, and how those results can be directly integrated into a wetland model. We'll be using VO Continuous to simulate groundwater for a wetland system. The focus here is simple. Generate groundwater data that reflects post-development conditions, then see how it changes wetland performance. All input data for this example come from the linked dataset. Our case study features a wetland with a contributing rural catchment. Under existing conditions, the wetland relies on recorded groundwater data to simulate its response. But after development, things change. Land use, inflow, and recharge patterns all shift. That means the old groundwater record no longer represents reality. So to model post-development accurately, we need simulated groundwater data. We'll look at two scenarios. First, without control, where part of the catchment is developed, and second, with control, where additional infrastructure, like a roof area and a route reservoir, is added. We'll compare results between the traditional approach that uses recorded groundwater and the new method that uses simulated groundwater. For existing conditions, the Nash-Hyde subcatchment has the following key properties. Area, 28 hectares. Curve number, 68. Initial abstraction, 8 millimeters. Time to peak, 0.66 hours. Soil texture, clay loam. Total porosity, 0.464. Field capacity, 0.31. Wilting point, 0.187. Saturated hydraulic conductivity, about 24 millimeters per day. This represents the baseline, or pre-development condition. At post-development scenarios, without control, the Nash-Hyde subcatchment is divided into two equal parts. One part remains as Nash-Hyde. The other part is represented by a stand-Hyde command to reflect the developed area. The stand-Hyde has an area of 14 hectares, a curve number of 70, and about 65% impervious cover. With control. In this scenario, we add another stand-Hyde to represent the roof area. That's about 1.75 hectares with nearly 99% imperviousness. A root reservoir is added downstream, and the previous stand-Hyde area is reduced to 12.25 hectares. This represents a post-development area with control measures. Across all scenarios, the wetland has the same characteristics. Initial water depth, 0.4 meters. Soil thickness, 1.5 meters. Hydraulic conductivity, 1,800 millimeters per day. Soil texture, clay loam, curve number 68. Initial abstraction, 10 millimeters. The model uses rainfall, temperature, evaporation, and groundwater data. But here's the challenge. For post-development, there are no observed groundwater records. So we'll use the new groundwater simulation tool to generate them. This avoids assuming that post-development groundwater behaves the same as before, which is rarely true. The process includes several steps. First, we begin by running the existing condition, the post-development condition, and the post-development condition with mitigation. Next, to consider changes in groundwater levels as a result of development, we generate simulated groundwater using the Wetland-Groundwater simulation tool. For this tool, you can use rainfall, evaporation, and flow data to predict groundwater levels for post-development conditions. The model is trained using observed groundwater data from 1991 to 2007 under existing conditions. The same rainfall and evaporation data are used for post-development, but with updated flow inputs that reflect new land use. Then, we rerun the wetland model with the new simulated groundwater input. We compare three conditions: existing, using observed groundwater; post-development, still using observed groundwater; post-development, using simulated groundwater. For each, we generate hydrographs showing wetland storage over time. We also plot 95% confidence intervals based on existing conditions. VO makes this easy. It automatically calculates and plots the confidence intervals. Now, let's use the groundwater simulation tool. To use the tool, you'll need two Excel datasets, training data, includes rainfall, evaporation, flow, and observed groundwater levels. Prediction data includes rainfall, evaporation, and post-development flow, but no groundwater levels, since those will be simulated. Here's how to set it up. Go to the Simulation tab and select Wetland Groundwater Simulation. In the Wetland Groundwater Simulation window, click the plus button to add a new simulation. Give it a name, and then select your training and prediction Excel files using the Browse buttons. Optionally, you can choose a specific wetland or leave it set to All. Define the output folder where results will be saved, and then click Start to run the simulation. If groundwater processing is enabled under the Home tab, you'll see the simulation progress at the bottom of the VO interface, including the simulation name, progress percentage, and file locations. Once the simulation is complete, VO generates several outputs to help you evaluate the results. It automatically adds the simulated groundwater data to your model. It also creates 4 CSV files: groundwater statistical summary.csv, performance metrics.csv, training data daily results.csv, validation data daily results.csv. And it generates 3 graphs comparing observed versus simulated groundwater, so you can easily evaluate model accuracy. Now, run the post-development condition using simulated groundwater data. Select the simulated groundwater level. The same process is then applied to the post-development scenario with control. Select the post-development condition scenario. Go to the Simulation tab and select Wetland Groundwater Simulation. In the Wetland Groundwater Simulation window, click the plus button to add a new simulation. Give it a name, and then select your training and prediction Excel files, considering the mitigation, using the Browse buttons. Optionally, you can choose a specific wetland or leave it set to All. Define the output folder where results will be saved, and then click Start to run the simulation. Now, run the post-development condition with mitigation using simulated groundwater data. To compare the results, you can select Scenario Comparison and choose Hydroperiod. This example demonstrates how groundwater simulation can improve the accuracy of wetland modeling under post-development conditions. You've now seen how to generate and apply simulated groundwater data in VO. For more details and advanced options, refer to the VO User Manual. As you continue working with VO, this tool will help you build more realistic and reliable hydrologic models.